Okay, I'm lecturing about the very basics of circuits. So this is all the prerequisite material that I would have to lecture about if I wanted a continuous set of lectures. And in the future, I wanted to lecture about systematic circuit solving techniques such as node voltage and mesh current. This is a lecture about circuits specifically for somebody who knows absolutely nothing about circuits, building up the theory of circuits absolutely from the ground up. So what is a circuit? Well, it's hard to find a real good definition of a circuit. A circuit is basically an arbitrary interconnect of circuit elements. I often read it said that a circuit is a closed loop. Well, in colloquial everyday speech, a circuit usually represents a closed loop. However, we often throw around terms like Thevenin equivalent circuit, where we're describing a network that isn't closed unless we put a load on it. So a circuit doesn't necessarily always, in the way we use the word, represent something that's closed. It's an arbitrary interconnect of elements, implied that current can flow from one element to the next and branch between the different elements in the network. So a circuit element is just some arbitrary thing. We haven't really described what that could be yet. For the purposes of this lecture, I'm going to pretend that circuit elements have two terminals. However, we have symbols for circuit elements that sometimes contain three terminals. And it's described by two measurable physical quantities. One of them is called voltage. The other is called current. Now, you can define these abstractly. You could say voltage is just some arbitrary property of this that says there's something different about one side of the element as opposed to the other, right? So 3 volts means that somehow this side is something that's measured by units of volts, and it's 3 of them higher than this side. More specifically, though, voltage is how much energy it takes to move charge from one side of the element to the other. So 3 volts means, defined in the way I've defined it here, putting a plus on the left side and a minus on the right side, means that it takes 3 joules of energy to move 1 coulomb of charge from this minus side to this plus side. Now, 1 coulomb of charge is a ridiculous amount of charge. There's a reason for that, which I'll discuss when we discuss current. So as I move that 1 coulomb across, I'm probably going to be changing this voltage. So you got to have some sort of machinery to pump out the charge as I move it. A better way to think of this is moving arbitrarily small charge, but the smallest amount of charge you can move is 1 electron. So you could think of this as it takes 3 electron volts of energy to move an electron from the plus side to the minus side. The reason why I switched the sides there is because the charge of an electron is negative. Okay, the next thing we have is current. So current has units of charge per unit time. So current is if I were to make some sort of surface here that the element penetrates, like I stick my hand there, in 1 second, say this were 3 amps, in 1 second, 3 coulombs of charge have moved across here. Now, I've said that a coulomb of charge is a lot of charge. Well, it's hard to charge an object to a coulomb of charge. A coulomb of charge, if an object is charged to that, would mean that there's 1 coulomb more positive charge in the object than there is negative charge. So it somehow sucked all the electrons out, and so there's a coulomb of charge, like an imbalance, where there's a coulomb of charge, more charge caused by nuclei than electrons. That's a very extreme physical state, depending on how big the thing is. However, motion of 1 coulomb of charge isn't really that big a deal, because we're not saying that there's a coulomb more charge in the element. We're saying that a coulomb of charge moved in the element. So you still have an even number of particles with positive and negative charges making up the element. It's just that the negative charges are moving this way. So 1 amp of current isn't really a whole lot of current. There's several amps of current being supplied that can be supplied by your laptop's power supply. However, 1 amp multiplied by a second, a coulomb, is a whole lot of charge. So the SI unit for current is the amp, and that kind of creates a bad unit for charge, but whatever. So we typically measure current in amps, milliamps, or microamps, and voltage in volts. 1 volt is 1 joule per coulomb. Let me think of, that seems correct to me. Yeah, 1 joule per coulomb. Cool. So now we know like how we describe these things. Keep in mind that this has meaning. This arrow has meaning. If I were to draw an arrow the opposite way and say 3 amps, that would mean the 3 amps would be going the other way. And if I were to draw the arrow this way and say minus 3 amps, these two things are the same. So in language of circuits, to turn right and then travel minus 1 miles is like saying turn left and travel 1 mile. They're interchangeable. Likewise, if I were to draw a minus here and a plus here and say this is minus 3 volts, these two things would mean the same thing. So if you tell me the voltage across this element is 3 volts, doesn't mean a whole lot to me. It means somewhat, because now I know the absolute value of the voltage across the element is 3 volts, but I don't know the polarity. I don't know which side it has the higher potential as opposed to the other, right? So I still need more information in order to tell what's going on, basically. Okay, so to go to what I was trying to go to before I went off on polarity, because I remembered I forgot to talk about polarity. Now that we know how to describe these, or like what these properties are, we need to build up a library of potential circuit elements. And this is a basic circuits lecture, so I'm going to only introduce a certain specific library of basic elements. So the first basic element I'm going to call the independent voltage source. An independent voltage source is defined in this way, that it specifies exactly and strictly what its voltage is. So for current we represent it with the letter I, voltage we represent it with the letter V. And it tells me absolutely nothing at all, this tricks students up, nothing about how much current is going through it. Current can go through it either direction and to any degree, right? So if you were to graph the amount of how much current can go through with respect to voltage, so a circuit element is often described by a function where I plug in voltage and I get out current. Sometimes it's a differential equation. They can get even more complicated than that. This is called the IV curve. If I were to draw the IV curve, which is the relationship between the voltage and current for this element, it would look like a vertical line located at 1 volt, indicating that the voltage is always 1 volt and the current could be absolutely anything. In order to figure out what the current is through this element, you have to solve the whole rest of the circuit and deal with what it's interconnecting with. The way I've drawn here, I've just drawn the element by itself connected to nothing. So, for reasons I'll explain later when I explain Kirchhoff's current law, the way I've drawn this, the current going through it is defined as 0. But if I connect it to something, like I connect some other element across it, now its current can be something else. So more things about independent voltage sources. Say I were to connect two independent voltage sources in series. Okay, what does series mean? Series means that the two elements are connected are basically touching each other. But there is no other element branching out in between them. So it means they're connected end to end, and they share these two ends uniquely with each other. You don't have anything branching out. Where two elements are connected together, we have a name for that. We call that a node. So you could say that if two circuit elements are in series, they share a node, and that node is shared with no other elements besides those two. So we're going to connect two independent voltage sources in series, which means we're going to connect them at one node, and we're going to connect nothing branching off between the two. Now, say this one is 1 volt and say this one is 2 volts. This says that it takes 1 joule of energy to move I misspoke. 2 joules of energy to move a coulomb of charge from here to here, and then 1 more joule of energy to move a coulomb of charge from here to here. So it takes a total of 3 joules of energy to move 1 coulomb of charge from one end of this all the way to the other. And I still know nothing about the current going through this. I have to solve the rest of the circuit. So these combine and make independent something that behaves equivalent to an independent voltage source that's sourcing 3 volts. My point is, if you connect two independent voltage sources in series, it acts with the same behavior. It's equivalent in behavior to an independent voltage source, which is sourcing the sum of those voltages. So independent voltage sources in series add. What happens if I connect independent voltage sources in parallel? What's parallel? Parallel is where elements share 2 nodes in common. So they both have the same endpoints. And it doesn't matter what else is connected to those nodes. As long as the elements share the same 2 nodes, they have the same 2 endpoints, they are connected in parallel. So the name should sort of make sense, right? Parallel means they're like parallel to each other. So they're going from, I don't know, it has nothing to do with geometric parallel, but they go from the same place to the same place. It's like they go the same direction or whatever. So if we connect them in parallel, you might get this is really confusing looking, because it's like, well, if it takes 1 coulomb of charge I'm misspeaking again, 1 joule to get a coulomb of charge from here to here, but 3 joules to get a coulomb of charge from here to here, but that's conflicting, because how many joules does it take to get the charge from here to here? And what you're discovering here is that not all possible interconnects of circuit elements make sense, right? So you, sir or ma'am, if you have drawn this, have drawn a circuit that does not make sense. And how you resolve this is you just never draw something like this. You can think of it in terms of like, well, what if we take the limit as a certain other circuit goes to this stage, and what you get is divergingly large thermal dissipation. So you catch things on fire, basically. You kill a puppy. Okay, so that's independent voltage sources. Now, independent current sources. An independent current source, we draw... Well, before I go on to independent current sources, I'm going to say a couple more things about independent voltage sources. So sometimes you see an independent voltage source drawn this way, as opposed to a circle with a plus and a minus in it. This is another legitimate way to draw an independent voltage source. And the origin of the symbol, well, the symbol resembles a voltaic pile, right? That's kind of the reasoning behind this symbol, which means it implies a battery. And batteries do behave somewhat like an independent voltage source, so some applications you might be able to approximate a battery as an independent voltage source. And when you do circuit design of devices that are powered by batteries, you start by considering your battery as an independent voltage source. Okay, now on to independent current sources. So an independent current source, we draw like so, and we specify a current. an independent current source tells me that defines the current going through me is always what I specify on the source. So labeling this I and V. And the voltage could be absolutely anything. I have to solve the whole rest of the circuit to figure out what the voltage is. So remember, independent current sources tell you nothing at all in themselves about what the voltage across them is. If I connect, well, first of all, you know that drawing I made where I drew a voltage source and I connected it to another voltage source, and I showed something that doesn't make sense. This also doesn't make sense, right? What I've drawn here in itself doesn't actually make any sense. I'll explain why later. So to make it make sense in itself, you have to close the loop. But it's okay to draw an independent current source just by itself. You just want to indicate the component. But there's something bothersome about looking at it just by itself. And we'll get to why later. Well, we're actually going to get to why now. Because what if we connect two independent current sources in parallel? Well, this is hinting at Kirchhoff's current law already. But we're saying that 2 amps of current is flowing, or 1 amp, 1 coulomb of charge is going this way every second. 2 coulombs of charge are going this way every second. So that means that 3 coulombs of charge have to supply both of these every second. And 3 coulombs of charge have to go this way every second. So if I have 2 independent current sources in parallel, then it behaves equivalently to 1 independent current source, which is sourcing the sum of those 2 currents. Similar to an independent voltage source, if I draw 2 independent current sources in series, and they're sourcing different currents, I have drawn something that does not make sense, and so I should not draw that. Now, I said that a battery behaves somewhat like an independent voltage source. There isn't something equivalent to a battery for an independent current source. We can combine elements and make a network that behaves like an independent current source, such as like a current mirror or some feedback system, but there's no like compact electrochemical device that behaves like an independent current source. An independent current source is almost always used as an abstraction of a larger, more complicated system that we're just sort of chunking down into one component to get the overall behavior to just describe something else using its overall essential behavior. Okay, what is a short circuit? A short circuit is a special case of the independent voltage source. It's equivalent to an independent voltage source that is sourcing 0 volts. So you can think of it as if we have an independent voltage source that's sourcing 0 volts. We don't bother writing the symbol for it and writing 0 volts. We just draw a line usually. An open circuit is a name for an independent current source that's sourcing 0 amps. So instead of drawing an independent current source and specifying it's producing 0 amps every time we have an open, which because there's a lot of opens in the world would be a lot of independent current sources, in fact infinitely many, we just draw nothing, right, to represent it. It's important though that you think of these two things like voltage sources that produce 0 volts and current sources that produce 0 amps. Next circuit component will be a resistor. So, a resistor is some device where the voltage and the current are linearly related once more, but their relationship is a line that goes through the origin, so that if you have 0 amps, then you have 0 volts, and vice versa. The slope of this line is called the conductance of the resistor. But more commonly, we define conductance as the reciprocal of resistance. So the slope of the IV curve is 1 over the resistance. So we can have, there's multiple ways to create devices that behave like this. You can make a cute little pill looking thing with bars out of graphite that very much behaves like this. It's something physical that we can model with a resistor, just like a battery is something physical that we often model with an independent voltage source. But also, a resistor can mean something that's not physical, like it's a linear approximation of a nonlinear element, or it's some sort of abstraction or some sort of distilling down of something more complicated. So, if you look up the circuit diagram and say the repair manual for your car, usually the resistors you would see in the circuit diagram would be real physical resistors that you could look at and touch inside your car. But it's not always the case. We use circuit notation to describe, well, anything and that behaves anyway. So, it can mean multiple different things. So we usually label the resistor with its resistance R, which usually we use the unit ohms to describe resistors. And 1 ohm is, well, this slope is current per voltage, so 1 ohm is 1 volt per amp. So you can think of it as, well, I won't go quite there yet. So sometimes you'll hear something referred to as Ohm's law. And Ohm's law is voltage is equal to current times resistance. Now this isn't a physical law because voltage doesn't always equal current times resistance. There are other circuit elements besides resistors, right? But we still call it Ohm's law for some reason. And a lot of physics textbooks make a big deal out of, well, they'll say like V equals IR is not the statement of Ohm's law. Ohm's law is something like, well, if a component is ohmic, then its IV curve is V equals IR. But that's just basically saying if it's ohmic, it's ohmic. It's kind of redundant. So Ohm's law is somewhat of an abusive language. But when we say Ohm's law, what we mean is voltage is equal to current times resistance. We can make this mnemonic device that is varsa T. So we draw a T inside a circle, and then we write VAR. Right? Now this is an abusive notation in itself, because here we have the symbol for resistance, and here we have the units for current. V is V either way. It would make more sense to make it like VIR or VA omega. The reason why we do it like this is because it makes an acronym. It says varsity. And then now that we have this symbol drawn out, let's say I want to know voltage. Well, voltage, I just cover up the voltage, is current times resistance. Let's say I want the, whoops, too many undos. Let's say I want the resistance. Well, resistance is voltage over current. And let's say I want the current. Well, the current is the voltage over the resistance, if that's useful to you. I just remember V is equal to IR. Okay, some more important things to say about resistors. I recorded farther on in the lecture and then realized that I forgot to say these things, and that was a real issue. So first of all, resistance is almost always a positive number. Any cute little pill resistor you buy from, I don't know, DigiKey, is going to have a positive resistance. The only case I could think of where you might encounter a negative resistance is if you are finding the Thevenin equivalent resistance of a circuit with a dependent source in it, and specifically circuits with dependent sources in them that are just solved as an academic exercise, right? So I haven't seen an amplifier with a negative output resistance. Secondly, Ohm's law requires a certain polarity, right? That is, that current follows voltage drop. What I mean by that is the arrow of current goes from the plus terminal to the minus terminal. Plus and minus being how voltage is defined, and the arrow being how current is defined. Right? So if I have a 1 ohm resistor, and this is 2 volts, I'm going to have 2 amps of current going this way from the plus to the minus. And this is related to the concept of passive convention, which I mentioned later and say I'm going to mention later. I've already mentioned this now. Okay. So we're not going to combine resistors in series and parallel yet until I talk about Kirchhoff's laws, but we'll get to that later. So what's my next component? Well, my next component is called a dependent source. So a dependent source, usually drawn with a diamond shape, is some sort of source that depends on some other measurable quantity somewhere else in the circuit. And these are usually used to make a linear approximation of some sort of amplification device, like a transistor. So I can say that the voltage across this is some gain, so it's always called a gain, times a voltage somewhere else in the circuit. And I can also draw a voltage that depends on a current somewhere else in the circuit, or a current that depends on a voltage somewhere else in the circuit, or a current that depends on a current somewhere else in the circuit. And we have these acronyms we throw around. We call this voltage that depends on a voltage-controlled voltage source. A voltage that depends on a current-controlled voltage source. A current that depends on a current-controlled current source. And a current that depends on a voltage-controlled current source. So if you see these in these four-letter shorthands, that's what they mean. Okay, Kirchhoff's laws. So, let's write down Maxwell's equations. That is, the curl of H is equal to J plus dE dt. The curl of E is equal to minus dB dt. The divergence of D is equal to rho, and the divergence of B is equal to 0. This is that the curl of magnetic, what the physicists call auxiliary field, like electrical engineers call this magnetic field, is equal to volumetric current density plus the change in time of electric field. The curl of electric field is equal to the negative of the change in time of magnetic field. The divergence of electric flux density, which physicists call something, I forgot what they call it, is electric charge density. And the divergence of B, which physicists call the magnetic field and electrical engineers call the magnetic flux density, is equal to 0. Now, the one that is there's a couple that are particularly important to me here, but the first one is divergence of E is equal to minus dB dt. That would mean that, not divergence, the curl, that integral around a closed loop of E dot dl is equal to minus the change in time of magnetic flux. Now this part, as it relates to circuits, is super important, right? And it's super important in some super contexts. But let's make an assumption about the circuits we're solving for the purposes of a basic circuits lecture, that nothing is changing in time. So that means all the voltages are constant in time, all the currents are constant in time, and all the charge density is constant in time. And if the currents are constant in time, then all magnetic fields are constant in time. And so change in time of magnetic flux is always zero, no matter which flux you're talking about. Now, when we go on to AC circuits, or circuits where these quantities do change in time, we continue to ignore magnetic flux. Because if you just ignore your problems, then they disappear. And then we deal with that later. So the purposes of the entire basic circuits topic or playlist, disregarding DC or AC, then we'll just pretend that dflux dt doesn't exist, and that will give rise to circuit or transmission line parameters like inductance per unit length or parasitic inductance or something, and so on later. So, but at least in DC, we know it's absolutely the case that the integral around the closed loop of E dot dl is equal to 0. And this is the same thing as saying the sum of all voltages around a closed loop is equal to 0, because voltage is a path integral of a line integral. Because there's a dot product here, it's actually technically a line integral. I misspoke. Voltage is the line integral of electric field, just as energy is a line integral of force, right? Voltage is energy, essentially. Electric field is force per coulomb. Voltage is energy per coulomb. And we have a name for this. We call it Kirchhoff's current law. I mean, wow, did I really misspoke there? Kirchhoff's voltage law. I wrote the sum of the currents is 0 and say Kirchhoff's current law. I do this a lot. So this is Kirchhoff's current law, or we abbreviate it KVL, which is even worse. If you think I accidentally say Kirchhoff's current law when I meant to say Kirchhoff's voltage law, I even more so can mess up and say KCL when I meant KVL. So I tend to just spell it out completely. So this means that if I have a closed loop of circuit elements, and this closed loop doesn't have to be just by itself, it could be a closed loop as part of a larger network, and it can contain any elements, or any number of elements, I'm just drawing 4 for simplicity, that the sum of the voltages across all of these elements is 0. Now, keep in mind, you have to define the polarities correct for this to make sense. So for it to make sense, the polarities all have to line up with each other or go the same direction. Which means that if you were to draw arrows from plus to minus on all these, the arrows would all go in the same direction. Or you could say that minus has to always be paired with plus. So it's like if I were to move 1 coulomb of charge around the circuit, then the voltage I'm defining is how much energy it takes to move that coulomb the same direction for every element. So it is 1 volt, it takes 1 coulomb to move it this way, right? And if this is 3 volts, it takes, 1 joule. 1 joule to move it this way. If this is 3 volts, it takes 3 joules to move it this way. And if this is 2 volts, it takes 2 joules to move it this way. And if this is, we have to make sure that Kirchhoff's voltage law is true now, is minus 6 volts, it takes minus 6 joules to move it this way. Cool, and that was obviously opposite the arrows all the way around. But it doesn't matter which way I draw the arrows as long as I'm drawing them all in the same direction. So if I were to redraw this, where I redefined my voltage such that this was no longer written with this polarity, but instead this polarity, then I can no longer say minus 6 volts here. I would have to say plus 6 volts, and now you notice that Kirchhoff's voltage law doesn't apply. If I add these together, instead of getting 0 volts, I get 12 volts. Right? So don't apply Kirchhoff's voltage law until the direction of your polarities of all your voltages agree with each other. So that's Kirchhoff's voltage law. So I don't know why I'm erasing all this. There's no need to. Let's go back to Maxwell's equations. Let me undo that erasing. So let's look at curl of H. We know that the divergence of a curl is 0, so the divergence of the curl of H is equal to 0. So that means that the divergence of whatever the curl of H is equal to, which is volumetric current density plus change in electric field with respect to time, is equal to 0, which means the divergence of J plus the change in time of the divergence of E is equal to 0, which means the divergence of J plus the change in time of volumetric electric charge density is equal to 0. Now, remember, we're assuming DC here, and we're going to later on assume DC to a fault. So we're going to ignore parasitic capacitances and high-frequency capacitances. So nothing's changing in time. So this is 0. So we have the divergence of J is equal to 0. Or, equivalently, the surface integral of J ds over any closed bag or any closed surface is 0. So if I have some sort of anything closed, all the total amount of current coming out of it will be 0. This means that, say I have some elements and they're connected together at some node. If I were to draw some surface around that node, the sum of all the current coming out of that surface would be 0. And because current only leads along the pathways of conductor that I've made, that I've drawn here in my circuit, that's how circuit notation defines things, then the sum of all the currents coming out of the node has to be 0. So Kirchhoff's current law, which I mentioned earlier by accident, is the sum of all the currents coming out of a node is 0 over the node. So back when I was talking about independent current sources, and I was connecting them in parallel, and I was saying, okay, if 1 amp goes this way, and 2 amps goes this way, 3 amps goes in this way, I was applying Kirchhoff's current law before I mentioned it. So those are Kirchhoff's laws. So now that we know Kirchhoff's laws, we can solve some basic circuits. Hold on a minute. So the first basic circuit that I'd like to solve is called a voltage divider. So let's say we have an independent voltage source producing a voltage I'm going to call V source, and it's connected in series with several resistors that are connected in series. How many? Well, arbitrarily many. So call this one R1, call this one R2, and call this one Rn. So I have little n resistors, and it makes a closed loop. Well, what if we wanted to find the voltage across just one of these resistors? Well, there's a trick for this. let's first figure out what the current is going through. Because if we know the current going through this resistor, then we can find the voltage because we just multiply by the resistance. Well, how do we do that? Well, say that because of Kirchhoff's current law, the current going through here must be the same as the current going through here. Right, I'll call this I source. And so, and this voltage here is R2 I source. And this voltage here is R1 I source. And so the voltage across the entire thing, V source, is equal to the sum of all of these individual voltages, which is the sum of Rn times I source, which is equal to I source times the sum of all of these Rn's. Right? And then now that and so the current is just our I source, it's just V source divided by the sum of my resistances. And I, of course, made some mistakes here. I made my subscript I, and then I made my subscript in. So now that I know my current, to find a voltage across each individual resistance, I just need to multiply by that resistance, because voltage is current times resistance. So V1, the voltage across the first resistor, is equal to I source, which is Vs over the sum over all the resistances, times R1. Or better is just write the ratio more clearly, R1 over the sum of all the resistances. Or V1 over V source is equal to R1 over the sum of all the resistances. As you can see, because voltage and current, voltage and resistance are on opposite sides of the equation, voltage goes like resistance. So voltage across an individual resistor over the total voltage is resistance of that individual resistor over the total resistance. So the ratio of voltages is the ratio of the resistances. And this is called voltage division. Right? So we have a name for this formula. We call it the voltage division formula. Or more generally, Vj over Vs is equal to Rj over the sum of all the resistances. And you can generalize this to, like, say I want this voltage, right? The voltage across the first two. Well, it's the first one, the first resistance plus the second resistance divided by the sum of all the resistances is equal to the voltage you wanted, I'll call it V12, divided by all the voltage, which is Vs. So I just glossed over something, and that is resistances in series. You just noticed, because it's trivial, that you can combine resistors in their behavior. So if you have two resistors with resistances R1 and R2 connected in series, again that means sharing one node but nothing else is connected to that node, then this is equivalent in behavior to one resistor with resistance R1 plus R2. Okay, so let's go on to current division. So say I have this sort of dual circuit, or similar circuit in concept to my previous circuit. That is, I have a bunch of resistors connected in parallel, and I have as many as I want. So it's supposed to be a 2 here. this is not written very well. I know what I was supposed to write, but it may be impossible to read later on. And we'll call the last one R sub n. And these are all connected in parallel, and they're all supplied by one current source. We now know that if we were to call this I1, call this I2, call this IN, that by Kirchhoff's current law, if we were to sum all the currents coming out of this node and set that equal to 0, applying Kirchhoff's current law, we would say that IS minus IS plus I1 plus I2 plus I3 dot 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 IN equals 0. So IS is equal to I1 plus I2 plus I3 plus dot 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 IN. Just like, I can add voltages when the elements are connected in series. Now that I've written out all these currents, I can apply Ohm's law with each of the resistors. But these two are the same two nodes, and so only have one voltage I can define here. And I'll call this, I don't know, V source. So I'm just having the same V source over again. So this is equal to V source over R1 plus V source over R2 plus V source over R3 and so on. Right? V source over Rn. So I source is equal to V source times 1 over R1 plus 1 over R2 plus 1 over R3 plus R1 over R4. So V source is equal to I source divided by the sum. I don't know why I've been using I equals 0, because I don't have a 0 resistor. The first one's a 1 resistor. You've been noticing that so far. Good for you. You caught me making a mistake. So 1 over Ri. So if I want to find the current going through just one of these resistors, so just I1 or just I2, for example, I1 is just the voltage across it, which is Vs, multiplied by or divided by R1. Sorry, I forgot my varsity. And that's just equal to Is, I1, is equal to, I don't know why I put an equals there, 1 over R1 divided by the sum, I equals 1 to n, of all of the resistances. Or I can write this as it's equal to Is times the conductance of the resistor of interest divided by the sum of all of the conductances. The unit 1 over ohms for conductance, we might call this the mho. We also call this the Siemens. It was named after a person named Siemens, just like ohm is named after a person named Ohm. So you often will see, so this formula here, we call it the current division formula. You often will see, because we like to write these formulas in terms of resistances, and people for some reason have this irrational aversion to complex fractions. We want to get rid of these fractions, right? So we would multiply the top and bottom by the product of all of the r's, right? So you would have something like I1 is equal to Is times the product of all of them but the one of interest. So I does not equal 1 of Ri divided by the sum of the products of I does not equal J of Ri, and we're summing over J, so J equals 1 to N. And in, say, the two resistor case, we would have a formula like I1 is equal to R2 over R1 plus R2, right? Or I2 times I source, of course, is equal to I source times R1 over R2 plus R1. And this should make sense because you know resistance sounds like it resists things. More current should go down the path of less resistance. So my current should go like the resistance of the opposite resistor. So if the opposite resistor is bigger, I get more current, right? So something that, again, I happened upon as I derived the current divider formula from the current divider circuit is resistors in parallel. So you may have noticed from that if I combine a bunch of resistors in parallel, their behavior is exactly the same as a resistor with resistance 1 over R1 plus 1 over R2 plus 1 over R3 dot dot dot, which is equal to the 1 over the sum of 1 over the resistances. Or, so I can call this R equivalent, or conductance equivalent is just the sum of all the individual conductances. Again, people don't really like this 1 over thing. So you'll see like the product of all of them over the product of all but each of them. This looks in the two resistor case. This looks kind of elegant. It says Req is R1 times R2 over R1 plus R2. That is product over sum. I don't really like this because, again, it doesn't really scale well to arbitrarily many resistances. It works pretty well with 2. If you try to do the same thing with arbitrarily many resistances, you get a product of all of them over the sum of products of all but each of them, right? Whereas this generalizes much better to more than 2 resistances. There's another resistance, I just have another 1 over that resistance in my denominator. This also works well, apparently, on reverse Polish calculators, if you're into that kind of thing. Okay, so that's voltage division, current division, resistors in series, and resistors in parallel. Okay, through much of my discussion of resistors in parallel and series, I often start sums at I equals 1, even though my first resistor is always R1. I mean, I always start the sums at I equals 0, even though my first resistor is 1. It's like a mistake that doesn't really have much consequences, but just to let you know, yes, I figured out I made that mistake. Let's move on to using resistors in series and using resistors in parallel to sort of back extract certain circuit, to like back solve circuits. So this is like the freshman physics way of solving circuits, and it's a terrible way to solve circuits, but we're going to have an example of doing it anyway. So say I have a source of 10 volts, and say, I don't know, I'm going to make up some resistances here, 10 ohms, and then 6 ohms, and then 4 ohms, right? And I want to find the current going through the 4 ohm resistor defined with this polarity. Well, this is the combining equivalent resistances way of solving this. And using voltage division and current division way, again from freshman physics. So the first thing we do is we combine all of these resistors into an equivalent resistor. So if we start with lumping these two together, And to do that, we say, okay, REQ is equal to the product over the sum, which is 24 divided by 10, which is equal to 2.4 ohms. And then we redraw the circuit, replacing those two resistors with a 2.4 ohm resistor. Then we combine these two resistances, saying REQ is equal to 10 ohms plus 2.4 ohms, which is equal to 12.4 ohms. And then redraw the circuit again, like so. This is 10 volts. Then we apply Ohm's law to figure out what this current is. And here we're going to encounter on something important called passive convention. We'll touch on that later. So we apply Ohm's law, and that's just 100 over 124 amps, which is equal to 25 over 31 amps. Then we apply voltage division to figure out how much of that voltage is across the 2.4 ohm resistor. But we already started these steps because we already got a current. So this voltage here, so V, 2.4 ohms, is equal to 25 over 31 amps times 6/5 ohms, which is equal to 30 over 31 volts, right? So about 1 volt. Trying to see if that makes sense. I mean, yeah, it seems to make sense. And then we do current. We then say, okay, now we have 30 over 31 volts here. So now we apply Ohm's law again to find this current. And this current is then 30 over 31 volts divided by 4 ohms. So let's call this the current I'm trying to solve current solution. So my current solution is, okay, again, 30 over 31 divided by 4 ohms, which is equal to 15 30-seconds of an amp. Okay, found a really silly mistake in post here. This is not supposed to be a 32 or a 31. It's supposed to be a 62. So make sure that you pick up on that. This entire section, at one point I was looking at it and thought the handwriting was kind of sloppy, but upon rewatching the footage I decided to keep it in and not re-record it. So I apologize if the handwriting during this segment was very sloppy. So I combined resistors in parallel. I then combined them in series. I then did Ohm's law, uncombined them in series, did Ohm's law, uncombined them in parallel, did Ohm's law again. Again, it's a horrible way to solve circuits, but in some instances you can get away with it if you know how to do Ohm's law and you know how to combine resistors in series and in parallel. It's easy to break this method. So say I have a network like this. Try combining resistors in series and parallel here. The answer is you can't, right? Because I can't find any situations where my resistors have the same two endpoints, they share the same two nodes, or they share a node and that node is not shared by anything else. So I have no situations where I have series or parallel here. And so I can't combine these resistors. And so I can't use the method I just described. Okay. So next method. Using Kirchhoff's current law and Kirchhoff's voltage law to solve a circuit. So say we had a circuit like this. This is 12 volts. I'm literally just making this up as I go along. 4 ohms. 6 ohms. 2 ohms. 10 volts. So I can just apply Kirchhoff's current law and Kirchhoff's voltage law directly to solve this. So let's define some things. Let's call this I1, call this I2, and call this I3, right? I know from Kirchhoff's current law that I1 plus I2 plus I3 is equal to 0. I know from Kirchhoff's voltage law that minus 12 volts plus this, again I have to line up all the voltage drops, so this, which is current goes with voltage drop. Again, I'll explain this later. It'll take a while. So plus minus 24 volts. Let's see here. Does that... No. I don't know what I'm thinking. Minus I3 times 4 plus I1 times 6 equals 0. Because the voltage around this loop, the voltages around this loop all add up to 0. And then I can look at this loop here and do the same thing. So I can say minus 10 volts minus I2 times 2 plus I1 times 6 equals 0. And now I have 3 equations and 3 unknowns. Right? I have this one, I have this one, and I have this one. And so I can solve for the 3 currents, I1, I2, and I3. So I'll do that. So putting it as a matrix, we have I1, I2, I3. Our Kirchhoff's current law says that we have 1, 1, 1, 0. Our Kirchhoff's voltage law here says we have 6, 0, minus 4, 12. Doing some quick algebra there. And then our other Kirchhoff's voltage law gives us 6, minus 2, minus 10. And then, well, I don't know why I'm saying minus 10. That's a 0. I'm dumb. Is equal to 10. And then we apply Kramer's rule, because that's my favorite way to do these things. Not very mainstream, but it still is. So D is equal to, I'm going to use the middle column, I guess, minus 1 times 0 plus 24 plus minus 2 times minus 4 minus 6, which is equal to minus 24 plus, let's see, this is minus 10, so plus 20, which is equal to minus 4. Okay, dx is equal to the determinant of this guy. Whoops. which is equal to minus 1 times 0 plus 40 plus 1 times minus 24 plus 0, which is equal to minus 40 minus 24, so minus 64. dy 6, 6, 0, 12, 10, 1 minus 4, 0 is equal to 1 times 0 plus 40 plus 1 times 60 plus 72, which is equal to 130 plus what's 172. dz is equal to 1 times 0 minus 24 plus 1 times 0 plus, wait, I gotta make sure I didn't mess up here. So 1 times 0 minus 24, so this should be a plus. Okay, 1 times minus, and this is a minus 1, times 0, this is 60 minus 72, which is equal to 24 plus 12, which is equal to 36. Okay, so that would mean that my I1 is equal to 64 over 4, which is 16. I2 is equal to minus 172 over 4, which is 40 minus 43, and I3 is equal to 36 over minus 4, which is minus 9. And I already know I made a big mistake because they don't add to 0. So then you'll have to watch me debug this. The one that I probably made the biggest mistake with is I2. So let me look at that again. Get out the red. So I have 1 times 0 minus 40, so 0 plus 40, plus 1 times 60 minus 72. And that's where the error is. I forgot the minus. So this should be 40 minus 12, which is just 28. So then I2 is minus 7. And those add to 0, so that checks. And then minus 12 plus 36, which is 24. Oof. Now I have other equations that are not checking. So I took some time to find my mistake, and I found out that this should be a plus here. The reason being is this minus 2 is in a odd position, and there should be a minus sign. If you remember this mask for determinants, plus minus plus minus plus minus plus minus plus. So then my determinant, my d, should be minus 44 as opposed to minus 4. And so these currents, I1, I2, and I3, should all be over 11. So 16 over 11, minus 7 over 11, and minus 9 over 11. And those should check. So you may notice that I made 2 dumb mistakes performing Simpson's rule. All right, not Simpson's rule, Kramer's rule. Simpson's rule is like a second order approximation for integrals. However, if I were to try to row reduce this, I would make even more dumb mistakes. So it turns out for me that even though I made 2 silly mistakes, this is the method that for me is the least amount of silly mistakes. Which means I make a lot of silly mistakes. Okay, so now I've covered the 2 very dumb ways to solve circuits. That is, combining resistors together in series and parallel, and then splitting up the currents and voltages thereof, and undo the combining of resistances in series and parallel to extract individual currents and voltages within, and just using Kirchhoff's current law and voltage law directly as you see them. Both of these ways are very inefficient, and there's much better ways to solve circuits. I won't do them now. I'll have dedicated lectures specifically for those ways. And I also covered those 2 ways of solving circuits very recklessly, quickly, loosely, and sloppily because my heart wasn't really into them. That may have caused a few problems for some people. But I want to move on to the topic of power. So what if I were to multiply current and voltage? What would the units be? Well, current is coulombs per second, and voltage is joules per coulomb. So current multiplied by voltage is joules per second, which is units of power. So what kind of power is this? Well, if I have a circuit element and so many coulombs are going by a second, and these coulombs are losing so many joules of potential energy, then there is energy exiting the circuit somehow, right? It's like if you have like a water wheel of sorts. And the amount of energy is just current multiplied by voltage. Now, what is passive convention? Passive convention is just like terminology, okay? So passive convention basically says the terms power, power dissipated, right? Or power received, depending on who you're talking to. So dissipated or received is defined as IV, where I'm mixing up my capitalized and lowercase i's just because it's DC, where I and V are defined such that current follows voltage drop, such that the current goes from the plus to the minus. Now, and that's all that means. Power supplied is always the negative of power received. So power supplied is always find power received with the minus sign, or current goes contrary to voltage drop. One or the other. So any element, well, so about power. So it turns out that resistors always receive power. What does that mean? It means that the power received by a resistor is always positive, right? So I times V is equal to I times R, which is equal to I squared times R, which is something positive because it's squared, multiply resistance, which is almost always positive. So power received by resistor is almost always positive. And to use Ohm's law, we require that the current must follow voltage drop. That means the arrow goes from the plus to the minus. So we define power, and we define power received, which is what's positive for a resistor, as power where you calculate it where the current follows voltage drop. So this is why it's called passive convention, because resistors are passive. Now, resistors always dissipate, unless it's a weird resistance that you get from some esoteric academic exercise that's negative. However, sources can either receive or supply power. So their power received can be positive or negative. So don't get all wound up into thinking that a source, just because it's called a source, is always supplying power. So the poster child for this is the simple circuit where I connect a independent current source and independent voltage source in a loop. Let's make it 1 amp and 1 volt. Now, say that I were to define my voltages and currents such that currents follow voltage drop. Well, for the voltage source, I know that this is 1 amp because it's 1 amp going around the loop, and that's already defined according to voltage drop. So the power received by the voltage source is 1 volt times 1 amp, which is 1 watt. It's receiving power, even though it's a source. So you can think of this maybe as like a battery being charged. Whereas, if I were to find the power received by the current source, I know because of the voltage source that this is 1 volt. I might change nibs. But the current as defined here is not following voltage drop. It's going from the minus to the plus. So to make it follow voltage drop, I just reverse it. So this is minus 1 amp going the other way. So the power received by the current source is minus 1 watt. And notice that these both sum to 0. So the current source is winning. It's pumping power into the voltage source. And just to top this off, I squared R is always also equal to V squared over R. So you don't need to find both the voltage and the current for a resistor. If you know one or the other, when you know the resistance, you know the power dissipated by the resistor. Okay, now that we've defined what power is, we have a circuit cycling technique involving power. That is the sum over all elements of a circuit of power received, which is IV, but all defined according to passive convention, is 0. Now there might be a way to prove this using conservation of energy and Maxwell's equations and how the Kirchhoff's laws come from Maxwell's equations, but if I were to prove this, I would do it just using circuit laws to keep things simple. And I have to make a decision here whether or not I want to try to do this proof before I introduced node voltages or after I introduced node voltages. And I think I'm going to do it now, but I'm going to call on something called node voltages. So basically, figure out what node voltages are in the future, and then come back to this video, and then you might be able to understand this proof. So I'm drawing 2 nodes here just for illustration and connecting a bunch of things to them. So say this node voltage is called VA and this one is called VB, right? I'm going to sum up the current times voltage for every single element. That is the sum for all elements of the current from, I'm going to 1 to 2, which is a local 1 and 2, so it's 1 and 2 just for that element, multiplied by the voltage at the node voltage V1 minus the node voltage V2, again, local to the element. So there's a different V1 and different V2 for each element, right? And this is going to, and I'm going to assume this is equal to something. I don't know yet because I haven't done the proof. Now, we're summing over all the elements. But for each place an element goes into a node, you get a term in the sum, right? So each element gives you two terms in the sum, one for each node. And for every node, every element connected to it makes a term in the sum connected to that node, right? So this is going to be the sum over all elements. This may be confusing, but I don't know any better way to explain it. Of, well, not all elements anymore. I'm going to change it to all nodes of either current coming out times its node voltage, V node, and this is current coming out for each of the elements connected to it. So it's all nodes, and then for all nodes it's sum over all elements connected to that node. Man, you must be so lost. I'm not lost though. Of either I out coming out into that element from the node times the node voltage, or I in the current coming in from that element times minus that node voltage. So the sum of all overall nodes of all elements connected to that node of one of two things: I out V times the node voltage, or I in times minus the node voltage. And this should have the same amount of terms up here, because this is all elements, and there's two terms per element. So the amount of terms is 2 times number of elements. And here I have all nodes, and for all nodes, all elements connected to them, but every element connects to 2 nodes, right? So this ends up being 2 times the amount of elements again, right? So both ways I have a term 2 times the amount of elements terms. Now, I out times the node voltage. So these are the same thing, right? So the sum of the currents going out of a node is 0. The sum of the currents going into a node is 0. If you mix them up, you got to change the signs so they're going all out or going all in, right? So this is equal to I out into that element times positive V node, right? And so this is equal to the sum over I out times V node summed over all the nodes. All nodes, which is equal to the sum of all nodes of 0 by Kirchhoff's current law, which is equal to 0. So the sum of all current times voltage over an entire arbitrary network, if I assume beforehand that I can use Kirchhoff's voltage law to justify the notion of node voltages, which I'll do in the future, I can sum over all of the coming ins and going outs of every node by every element, and by Kirchhoff's current law, I get 0. And this is the law of conservation of energy, but let's just not accept it because energy is conserved. Let's just prove it. So that may be really confusing. I'm not sure. But I'll move on, because what else can I do? Okay. So now that we have power, what do we do with it? Well, sometimes you get these circuit solving problems where you get these elements connected together. And usually there's a lot of them. And I'm just making this up on the fly. And sometimes you get the power supplied by some of them. So, or received, or yeah, let's this one say this one supplies 2 watts. And let's say this current is 1 amp and this voltage is 1 volt. And this thing, I don't know, receives a watt. And this thing still has 1 amp because they gotta follow Kirchhoff's current law still. and the voltage across it is, I don't know, 2 volts. And now I have to make sure that I don't, and say this one, I don't really constrict myself by Kirchhoff's laws too much. Like, 1 amp goes here, if I define this current, now I define that current, which I define this voltage, because I define this voltage, which I define this power, defines a current, and they can't contradict. So I'm just going to avoid this, I'm just going to define more powers. To try to avoid conflict in the given information, which is something that happened when I was taking basic circuits. So it's an easy trap to fall into when just making up circuits problems. So I want to find this power received question. Call it P. Well, the sum of all the power receives is equal to 0. You can also do the sum of all the power supplied is equal to 0, because you're just changing the sign of both sides of the equation, and you change the sign of 0, you just get 0. So I'm just going to set up the power receives, though. So that would be 2, that would be P, the one we don't know, 2 watts received, plus 3 watts supplied, which is minus 3 watts received, plus 1 watt received. I'll just put the watts in. 1 watt received, minus 2 watts supplied, so plus minus 2 watts, because it's supplied. And then this here is minus 1 watt received. Why? Because the current is not going with voltage drop. So if I were to multiply current and voltage here, I get power supplied, but I'm summing up all the power received. So this is like sum of power received, just to remind you. So I need to change the sign to make it power received. This here, the current is following voltage drop, so the power received is indeed minus 2 watts, and I don't have to put a minus sign or anything. I mean, it's positive 2 watts. The polarity minus got sucked into the volts for me. That happens too, that's really embarrassing. All equals 0. And so then we just add this up. P is equal to 2, minus 1, 0, minus 2, minus 3, minus 1, move it to the other side, 1 watt. Hopefully I didn't make a stupid mistake in there. Yeah, okay, good. So sometimes you see problems like that, and that's how you do them. Next thing I would do with power is called maximum power transfer. So this is a subject people sometimes get obsessed with, because it has to do with impedance matching into transmission lines. So say I have a resistor we're going to call RT for reasons unknown, and this we're going to call just VS. You call it VT, but let's call it VS. And then we have a resistor here we call R load, right? If the problem is this, if we fix RT and we fix VS, how can we we can vary RL? What RL do we pick that maximizes the power dissipated by RL? Which means that given this voltage, and given that it has to have this resistance attached to it, what resistance do we put on so that we can get the most power out of that source? So let's just find an expression for the power. So we need the current, and we need the voltage. So for the voltage, we just use V load. We just use voltage division. So that's just R load over R load plus RT times VS. For the current, we just use Ohm's law. So current through the load, this is I load, is equal to VS divided by RT plus RL. Remember that VS is across both of these resistances. So I need to divide by both of these resistances, right? Copy the voltage around to get the current going through. And then the power is voltage times current. So power in the load is VS squared, right, times R load over RT plus R load squared. So you see that the numerator goes up with our load, and the denominator also goes up with our load. But if our load is 0, then your power is 0. As our load goes to infinity, well, the denominator is squared, so it wins, and so the power also goes to 0. So how this is optimized is somewhere in between. So we can either maximize this, or we could minimize its reciprocal. It's easier to minimize its reciprocal. Because Vs is fixed, we can ignore it. So we're just trying to minimize the expression RT plus RL squared divided by RL. So we'll take derivative with respect to RL, and that's low d high minus high d low divided by low squared. And I want to set that equal to 0. We presume that this is not going to be where the minimum is, because that makes the power 0. So presume at the minimum this is not 0, and so we can multiply both sides by it. So we get 2RL times RL plus RT is equal to RT plus RL squared. And so this initially intimidating looking algebra really isn't that intimidating. It's that it reduces to 2RL. It's just equal to RT plus RL, and so RT equals RL, or RL equals RT. So maximum power transfer is the principle that if RT is fixed and Vs is fixed, and I can only vary RL, that to maximize the power dissipated by RL, I need to make it equal to the source resistance RT. Now I might go check, is this really a minimum? Trust me, it's really a minimum. Engineers don't care about the math. We can tell if it's a minimum by just looking at it. Okay, it's a minimum. So this truly, RT is equal to RL truly does maximize this expression. Cool. Some traps that you can get into is, what if we were to fix the wrong resistor? So let's say, or fix a different resistor than the one we're trying to maximize the power dissipated by. So let's say we're trying to vary RT to maximize the power dissipated by RL, right? That's a different problem, because the resistor we're varying is different than the resistor dissipating the power. And it's actually really simple. The resistor that we're varying in that case has to be 0. Because power in a resistor, dissipated resistor, is V squared over R. So if you can maximize the voltage across that resistor, then you can maximize the power dissipated by it. So in the case we were varying this resistance, if we made the resistance really, like, we were varying the R as well as the V. But if you vary a different resistance than the one you're dissipating power by, you're varying just the V. And so you just want to make the V as big as possible. So you want to just make this expression as big as possible. So just make this 0. Right? Okay. Hopefully that's clear. So what do I have left after power and passive convention and maximum power transfer? I believe I only have one thing left, and that is these dumb problems. So sometimes you'll encounter problems in academia where you're given a graph of current with respect to time, and there's some finite, there's like increments on it. And you're asked to make a graph of charge, like just charge, I guess, Q, with respect to time. And you're given something initial condition like Q at time 0 is equal to 0. And your graph you're given might be something like, let's make this 1, let's make this 2, let's make this minus 1, let's make this minus 2, let's make it go up to 1, and then make it go down to minus 2, and then we'll make it go back to 1, and they'll have like a triangle shape. And then we'll make it go like this, and then down to -2, and then go over, and then come up again, and then have like a triangle shape. Okay. So this has a bit of a history with me. So if you don't have these slopes here, then it's very trivial just to look at this current graph and find the Q graph. By the way, this is like if you were to like put current into some bag, like into a bag, and you had some sort of reservoir to hold charge here, like a giant piece of metal, and you're just pumping current in, and the current has no way out. You're finding the charge inside the bag. The charge is just simply the time integral to current. Now, if you don't have any slopey parts, then this is really easy to do just by eyeballing it, right? The current is the slope of the charge. So you just go slope, 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 slope. However, TAs may often take off points because you didn't show any work, even though it's trivial and it doesn't require any work. So if you're a TA that tends to like to take off points for not showing work on problems where you find Q with respect to time given an I with respect to time, and you just do an integral, and I is just a piecewise constants, repent. But anyway, I decided to make this one a little bit more difficult for example reasons and put these like slopes in here. These both have slopes of 1. These have slopes of 1. Because they sometimes trip up students. So we'll start with, we see Q at time 0 is 0, right? So we're integrating this, so the value turns into a slope. So it has a slope of 1 for 2 units of time, right? So like this, we'll cover, maybe this is in seconds. So it goes up to 2 because it has a slope of 1 for 2 units of time, right? Then it has a slope of -2 for 1 unit of time. So it goes down back to 0 in the next unit of time. Then you have this slope, right? Well, we know that it's going to go up like the integral of a line is a parabola. We also know that because the slope is 1, the leading term of this quadratic equation will be 1/2 t squared, so that turns into a slope of 1. So we know it's going to go up from here, and it's going to go up like 1/2 t squared, starting here as if this were 0. So after 1 unit of time, it's going to make it up to 1/2. So say this is 1, say this is 1/2. And that should make sense because the area underneath this is 1/2. So it should get to 1/2 at the end. So this is like 1/2 t minus 3 squared if you want the algebraic expression for it. Then from here, we start all over again. Now, I, for some reason, in my short thinking, decided to create an expression for I of t that did not have an average value of 0. So, every time I go through the cycle, I pick up a 1/2. This is very dumb. Usually, you don't have this. But anyway, so now I have a slope of 1 for 2 units, so I go up to 2.5. So I go up to 2.5. I then have a slope of -2 for 1 unit, so I go back down to 1/2. And then I have another parabola that takes me up to 1. So I go all the way down to 1/2, and then a parabola that takes me up to 1. And so on and so forth. And so if you want an algebraic you want an expression for this, this would be 1/2 t minus, let's see, 1, 2, 3, 4, 5, 6, 7 plus 1/2. So that's how you go about those kinds of problems. If you really want the grotesque work of it, I'll oblige for a second. So Q is equal to the integral from -infinity to t of 1 dt, right, for this region, which is equal to t, let's see, yeah, these have to, this has to be d tau, this has to be done with a variable tau, evaluated at t and minus infinity, which is equal to t minus, and then you have to deal with, okay, what was the integral from minus infinity to 0? It was 0, right? So we should actually make this a 0. Man, this is really sloppy. And just utilize that q of times 0 was 0, so then this just becomes t, right? And so that's why this is a t. Okay, so to continue this, I would say that at the region from 2 to 3, q is equal to, well, whatever it was at time 2, which was 2, plus the integral from time 2 to whatever time t of the value of I, which is minus 2 d tau, which is equal to 2 plus minus 2t evaluated from, or minus 2 tau, that is, evaluated from t to 2, which is equal to 2 minus 2t plus 2 times 2, right? Which is equal to minus 2t plus 6. So if I were to plug t is equal to 2 into here, I would get 2. So it starts at 2 at time t equals 2 and decreases by a slope of minus 2. And to keep going with this, say q from time 3 to 4, so I don't know, 3 to 4, is equal to whatever it was at time 3, which appears it's 0. So 0 plus the integral from 3 to t of this function in here, which is tau, but with a y-intercept, and you can tell that the y-intercept is going to be minus 3. So tau minus 3 d tau, which is equal to 1/2 tau squared minus 3 tau evaluated from t to 3, which is equal to 1/2 t squared minus 3t minus whatever you get if you plug 3 into this, which is 9/2 minus 9, which is minus 9/2, so plus 9/2, right? And you can complete the square and get this, right? And that'll tell you how exactly you plot the parabola. Okay, with that I'll end there. Pretty fast, pretty sloppy, pretty laborious. I know I sound bored through the whole thing, but the reason why is, well, I'll have to confess I was, right? This is material you have to go through to get to the material that's interesting, and as a result, it's very tempting to lecture on this material very fast and boredly and not take time to figure out when students don't understand when they don't understand. So I could have solved this problem, but in the course of my lecturing, it seems like I really didn't. I just fell into the trap once again. But again, YouTube has feedback mechanisms in it. If this will be posted on YouTube, we still don't know. If you're watching this on YouTube, use the feedback mechanisms, because I understand people don't unless you remind them that they're there. If my handwriting was too sloppy, tell me my handwriting is sloppy. I already know that. And that's it.